Hi, my name is Mr. Peck from Ideas Inc. School, and today we will be discussing the various separation techniques. Let's begin by stating some of the differences between a compound and a mixture. Compounds are pure substances that can only be separated by chemical means, while mixtures are impure substances that can only be separated by physical means. But how do we test to see if a substance is a compound or a mixture? We can perform two simple tests. The first test is to determine the melting or boiling point of a substance. If the substance have a fixed melting or boiling point, it is a compound. However, if the substance is a mixture, which is an impure substance, it will melt or boil over a range of temperatures. The second test is chromatography, which we will go into more details by the end of the chapter. For now, if a substance is a pure compound, we will see only one dot appearing on the chromatography paper. And if the substance is an impure mixture, multiple dots can be seen instead. We will begin with the first technique known as filtration. This method is used to separate an insoluble solid from a liquid. For instance, when a mixture of sand and water is passed through a filter paper. The sand is too large to pass through the filter paper, hence it will be left behind as a residue. On the other hand, the water molecules are small enough to pass through the filter paper as a filtrate. The next separation technique uses a separating funnel. This method is used to separate immiscible liquids. Immiscible liquids are substances that cannot dissolve and mix with each other. For instance, water and oil are immiscible liquids. Other factors to consider when using this method is whether the liquids have different densities and whether there is a clear distinct boundary between them. When the valve is turned on, the denser liquid flows out into a receiving flask and the valve is turned off once the boundary between the liquids is reached. This leaves the less dense liquid in the funnel. The next method of separation uses magnets. Magnetic materials that contain iron, nickel and cobalt can be attracted by magnets. Thus, when separating a mixture of sand and iron filings, we can use magnets to attract the iron while leaving the sand behind. The next method of separation involves sublimation. Substances like ammonium chloride and iodine can sublime. Recall that when a substance sublimes, it changes from a solid state to a gaseous state. We can use this technique to separate a mixture of iodine and salt. You can pause the audio and refer to the diagram in the notes to have a better understanding of the setup. When this mixture is heated, only the iodine will sublime. Solid iodine changes into iodine vapor and rises. A hot iodine vapor condenses on the cooler surface of the inverted filter funnel and changes back into solid iodine crystals. The next two separation techniques involve trying to extract the dissolved solute from its solution. There are two methods to do so. Number one is evaporating the mixture to dryness. And number two is to perform crystallization. In a salt solution, the salt is known as a solute while water is known as the solvent. Let's start with evaporation to dryness. When a mixture of salt and water is heated, salt crystals will be left behind when all the water has been evaporated. Please note that this method only works on non-colored solutes that are very stable to heat, meaning that these substances do not decompose easily when heated. Therefore, evaporation to dryness cannot be used to extract sugar because it can decompose easily when heated. And this method cannot be used to extract blue copper sulfate crystals because prolonged heating will produce white anhydrous crystals instead. This is because heating the mixture for long periods of time will remove the crystal's water of crystallization. The advantage of using evaporation to dryness is the possibility of extracting all the dissolved solutes, thus having a high yield. But the disadvantage is that this technique can only produce small irregular crystals. Lastly, if the mixture contains a flammable liquid like alcohol, these liquids can catch on fire easily when exposed to a naked flame. Thus, make sure that a water bath is used to prevent direct heating. The other technique we can use to extract the solute is crystallization. The advantage of using this technique is the production of larger and more well-defined crystals. However, the disadvantage is that there will still be dissolved solute left behind in the solution, thus the yield will be lower. The principle behind crystallization is the solute having different solubilities at different temperatures, meaning that some solutes have higher solubilities at higher temperatures and lower solubilities when temperatures are lower. It is due to this difference that allows crystals to form in the solution. The only solute that is an exception to this rule is sodium chloride. This solute has similar solubilities over a wide range of temperatures, thus crystallization cannot be used to extract it. Evaporation to dryness have to be used instead to extract sodium chloride crystals. In order to perform crystallization, we first heat the solution till saturation. This is usually achieved by heating the solution to half its volume. We can check for saturation by dipping a glass rod into the solution. If the solution is saturated, crystals will form on the rough surface of the rod. Once a saturated solution is achieved, The mixture is then cooled to allow crystallization to occur. The mixture is then filtered with a filter funnel and paper. The crystals will be left behind on the filter paper as a residue. These crystals are then washed with some cold distilled water and later dried between sheets of filter paper. The next separation technique that we will be discussing is simple distillation. This process involves separating the solvent from its solution. For instance, in a salt solution, this technique allows us to extract the water while leaving the salt behind. Please pause the audio to refer to the diagram in the notes for a better understanding of the setup. Let's begin. When the solution is boiling, only water changes to water vapor and rises. The hot water vapor then enters the condenser where it cools down and condenses on the cooler internal surface area. As a result, pure water will drip out of the condenser as a distillate. While performing distillation, we have to take note of a few precautions. Boiling chips are used to ensure smooth boiling by preventing large bubbles from forming. The bulb of the thermometer must be placed at the mouth of the condenser to accurately measure the boiling point of the distillate. When setting up the condenser, we need to make sure that the cold water enters from the bottom. This ensures maximum internal surface area cooled by water, thus maximizing the available surface area for condensation. This also ensures that the end of the condenser is the coldest part of it, thus all the vapor will eventually condense by the time it reaches the end. We have to make sure that the condenser is tilted downwards towards the receiving flask to ensure that the distillate does not flow back to the distilling flask. Lastly, we have to ensure that the distillate is not blocked by a stopper from entering the receiving flask. The next separation technique is known as fractional distillation. This technique is used to separate miscible liquids with different boiling points. Miscible liquids are substances that can dissolve and mix with each other. For instance, ethanol and water are miscible liquids with different boiling points. Ethanol boils at 78 degrees Celsius while water boils at 100 degrees Celsius. This technique can also be used to separate the components of crude oil and to extract ammonia during the Haber process. Please pause the audio and refer to the diagram in the notes for a better understanding of the setup. Let's begin. The main difference in the setup between fractional and simple distillation is the addition of the fractionating column. A new column is filled with small glass spheres to provide a large surface area for the gas with the higher boiling point to condense. At the same time, this allows the gas with the lower boiling point to remain in gaseous form, pass through the fractionating column and enter the condenser. As a result, the fractionating column allows the gases to be separated based on their boiling points. For instance, in the mixture of ethanol and water, ethanol will boil first as it has a lower boiling point. However, as the ethanol boils, water is also evaporating. Thus, both ethanol and water vapor will enter the fractionating column. In the column, water vapor which has a higher boiling point will condense and drip back down while ethanol vapor continues to rise and enter the condenser. Therefore, ethanol is collected as the distillate first, and when the temperature registered by the thermometer reaches 100 degrees Celsius, water will then drip out as the distillate. The precautions of fractional distillation is similar to that of simple distillation. However, it is inevitable that the ethanol collected will contain some traces of water. When that happens, the water can be removed by adding some anhydrous crystals to absorb the trace amounts of water. The water collected can sometimes also contain traces of ethanol. When that happens, ethanol can be removed by gently heating away the volatile liquid. Also note that glass beads are used in the fractionating column because it can withstand high temperatures without melting. Now we will move on to the last separation technique known as chromatography. This technique is mainly used to identify substances in a mixture or to test for the purity of a substance. The principle behind chromatography involves different substances having different solubilities in the same solvent. The more soluble the substance is in a given solvent, the further it will travel from the starting line. You can pause the audio and refer to the diagram in the notes for a better understanding of the setup. Let's begin. The setup you see in the notes is the ascending method of chromatography where the solvent is allowed to move up the paper. Note that if no dots appear on the paper, there can be two possible outcomes. First, the sample might not be soluble in the solvent. Thus, the solvent can be changed from water to ethanol or oil instead. Secondly, the dots might be colorless. Thus, a locating agent can be sprayed or UV lights can be used to locate the dots. While performing chromatography, we have to take note of a few precautions. We need to use a pencil to draw the starting line and the solvent front. Pencil markings are insoluble and will not smudge, while pen ink will smudge and interfere with the results, making them unreliable. The solvent front is the maximum distance that the solvent can travel up the paper. This maximum distance is due to gravity and evaporation. The solvent front must be seen to ensure that the length of paper used is long enough to accommodate the entire separation process and that all the dots can be visible. Next, the starting line must be above the solvent level. This is to prevent the sample from dissolving into the solvent and not separating as a result. The sample size must also be small to ensure that the separation produces small distinct dots while avoiding the production of large dots that overlap. The setup should also be encased in a closed container to prevent the loss of solvent due to evaporation. And lastly, if we want to speed up the process, the descending method can be adopted. In this alternate method, the solvent is allowed to move downwards with the assistance of gravity. This will increase the speed in which the solvent moves across the paper, thus speeding up the separation of the sample. However, a longer chromatography paper needs to be used as the solvent front will be located further away from the starting line. Next, we will move on to the advantages and applications of chromatography. While performing this technique, only a small amount of sample is required. The separation occurs quickly and accurately, and this process can help identify the substances present in a sample. That is why chromatography is used to test ink used during forgery cases. This technique is also used to test food for poisons and toxins. Lastly, this technique can be used to test urine samples to catch doping athletes during sporting events. We have come to the end of the chapter. Fortunately, some schools do teach students how to calculate the RF values of a sample. Continue listening to this section if it is relevant to your syllabus. If not, thank you for listening and have a nice day. You can pause the audio and refer to the diagram in the notes for a clearer understanding. Let's begin. The RF value of a substance is the ratio between the distance traveled by the solute to the distance traveled by the solvent. The distance traveled by the solute is measured from the starting line to the final position of the dot, while the distance traveled by the solvent is measured from the starting line to the solvent front. As a result, the more soluble the substance, the larger the RF value. If calculated correctly, the RF value will always be a number that is less than 1. We can use these values to identify the components of a sample more accurately, as substances with the same RF values are most likely to be identical. However, please note that RF values can be affected by solvent and temperature. This is because substances have different solubilities in different solvents and particles diffuse faster as temperature increases. We have finally completed the chapter. If you have any doubts, please approach Mr. Peck. Thank you for listening and have a nice day.